Bem-vindos ao nosso espaço, um mergulho profundo nos assuntos mais interessantes de esportes, ciências e temas gerais do momento. Aqui você vai encontrar conteúdo de qualidade, com análises empolgantes e descobertas fascinantes que vão expandir seus horizontes. Nossa missão é trazer informação relevante de forma dinâmica e descontraída. Queremos que você faça parte dessa jornada incrível de conhecimento e diversão. Se gostar do nosso conteúdo, não esqueça de deixar seu like e se inscrever no canal para não perder nenhuma novidade. Ative o sininho também. Aproveite!
If you love science, don't forget to like and subscribe. Take a deep breath. Whether it's the aroma of fresh coffee, the scent of a blooming rose, or the sharp tang of a lemon, your sense of smell is your most direct link to the chemical world. For decades, biology textbooks have told us a simple story. Smell works like a lock and key. A molecule travels through the air, lands in your nose, and if its shape fits into a specific receptor, a signal is sent to your brain. It's elegant, intuitive, and, according to a growing number of physicists, it might be fundamentally incomplete. Welcome to the world of quantum biology, where your nose isn't just a chemical sensor, it's a sophisticated spectrometer utilizing the strange phenomenon of quantum tunneling. To understand why the shape theory is under fire, we have to look at its failures. There are molecules with almost identical shapes that smell completely different. Conversely, there are molecules with wildly different shapes that smell exactly like rotten eggs or bitter almonds. If shape were the only factor, these anomalies shouldn't exist. This is where the vibration theory of olfaction comes in, popularized by biophysicist Luca Turin. This theory suggests that our noses aren't just feeling the shape of a molecule, they're listening to its music. Every chemical bond in a molecule vibrates at a specific frequency. These vibrations are like a signature, a unique chord played on a molecular guitar. But how does a biological receptor hear a vibration? This is where the quantum magic happens. In a lab, scientists use a machine called a spectrometer to identify substances by measuring their internal vibrations. It works by using a process called inelastic electron tunneling. In your nose, the theory posits that the olfactory receptor acts as a tiny electronic circuit. Imagine an electron on one side of a receptor wanting to jump to the other side to trigger a nerve impulse. Normally, there is an energy gap that the electron cannot cross. It's like a ball trying to roll up a hill it doesn't have the speed for. In the classical world, the electron is stuck. But in the quantum world, particles can tunnel through barriers they shouldn't be able to cross, provided they have a way to lose exactly the right amount of energy. When a scent molecule enters the receptor, if its internal vibrations match the energy gap the electron needs to overcome, the electron can drop its excess energy into the molecule's vibration and tunnel across the gap. This flow of electrons, a tiny current, is what triggers the signal to your brain. If the vibration doesn't match, the electron can't tunnel, and you don't smell that specific scent. Essentially, your nose is performing a quantum measurement of a molecule's energy levels. This makes your nose a biological spectrometer, scanning the infrared frequencies of the world around you without using light. One of the most compelling pieces of evidence for this quantum theory involves isotopes. Consider hydrogen and its heavier cousin, deuterium. Chemically and structurally, they are nearly identical. Molecules made with deuterium have the exact same shape as those made with normal hydrogen. According to the lock and key model, they should smell identical. However, in controlled experiments, fruit flies can easily distinguish between heavy and light versions of the same scent molecule. Even humans have shown the ability to differentiate between deuterated versions of certain musks. Since the shape hasn't changed, but the vibration frequency has, because heavier atoms vibrate slower, this points directly toward a vibrational, quantum mechanism for smell. This shift in perspective is part of a larger revolution called quantum biology. For a long time, scientists believed that the warm, wet, and messy environment of living cells was too chaotic for delicate quantum effects to persist. We thought quantum mechanics was reserved for subatomic particles in high-tech cold labs. Yet, nature has had billions of years to master physics. From the way birds navigate using Earth's magnetic field to how plants harvest sunlight with near-perfect efficiency, we are discovering that life is quantum optimized. Our sense of smell might be one of the most accessible examples of this. When you smell a perfume, you aren't just detecting a shape. You're witnessing an electron vanish from one spot and reappear in another, assisted by the rhythmic dancing of atoms. Understanding the quantum tunneling of smell isn't just a win for theoretical physics. It has massive practical implications. If we can crack the code of how receptors translate vibrations into signals, we could build electronic noses, far more sensitive than any dog's snout. These devices could detect the vibrational signature of diseases like cancer or Parkinson's on a patient's breath long before traditional tests find anything. We could revolutionize the fragrance and food industries, designing scents by calculating their physics rather than through trial and error. Our noses are proof that the line between chemistry and physics is thinner than we ever imagined. We are walking, breathing quantum machines, sensing the invisible vibrations of the universe one breath at a time. For more incredible facts like this, don't forget to subscribe and turn on notifications.